Yay. Okay, fine. Let's get going. So I'll start with just a couple of slides that show, I guess, motivation for why we want to build these sort of distributed systems and resilient systems, and then we'll get straight to more architectural diagram. No, only kidding. We're going to get down to code. Okay, so what is this thing? This is actually, don't worry, I'll have links at the end. So there was a really interesting paper that talks about failure modes of data centers. So let's imagine now, in this room, we're all software engineers, but let's imagine that our code is perfect, never fails, always runs. And there's a whole bunch of stuff above it, right? There's this internet thing, and then you have routers, you have load balancers, you have aggregators, you have top-of-rack routers. And underneath it, those four, orange things, that's our software. That's brilliant. That always works. So how about this other stuff? How often does that fail? Surprisingly often. Now, you might be saying, oh, come on, I've only seen one, maybe two failures in my systems. But even if your code is perfect, if you have sufficient number of, any one of these things, something's going to go horribly wrong. Now, so these are the probability of failures. Of course, how long does it take to repair? That's your next question. I guess the easy one is a week later. A week later, everything works. Now, that's probably not the kind of SLA you want to give to your clients. Don't worry, we're going to fail, but a week later, we're going to have it fixed. It gets much more interesting as you get to the units of minutes, units of seconds. So again, the probability of everything being repaired in a couple of minutes is actually very low. So your software, which is perfect, don't forget, had better be able to deal with all of this stuff. Now, again, what is the root cause of failure is in this chart. And again, assuming your software is perfect, the failure happened because the stuff above it broke for these reasons. So you might be looking at this thinking, well, okay, that's actually pretty depressing, right? Things break actually quite often. They take a long time to repair. And we have to assume that our software is perfect. That doesn't feel quite right. So what can we do about it? Well, let's take a look. Let's build up this system of small components and really see what can be done. Okay, so let's begin with this. I'm going to take an IoT-like example, and we're going to have a device, this really unreliable thing sitting behind some unreliable network, and we're going to implement a shadow in front of it that represents the device's state, and the shadow is responsible for pushing the commands to the device in a reliable way. And you might be thinking, well, this is kind of cool. The device is nice. Maybe we've written it, and you can go to the IBM stand, have a look at some of those fancy Arduinos and Raspberry Pis. It's all fantastic, right? And then, but this is the cool stuff, right? This thing, the device has an API, and we have this really cool reactive component in front of it. And because it's a reactive component, we say, you know what, we're going to be non-blocking, we're going to have back pressure, we're going to have all those things. We're going to do Akka HTTP, right? The device talks HTTP, and so our component is going to talk over HTTP to it. And so we're going to create this Akka HTTP flow, which gives us asynchronous execution, gives us non-blocking back pressure. We're going to pipe these commands to it, but remember, they're asynchronous, right? So they can arrive, the responses can arrive at any time, so we need to tag them. We're going to tag them with a string. That's okay for now. And then we're going to create this tag and the request. We're going to run the request with the tag that we've created through this flow. And then in here, we're going to write some logic that handles the response. This is the cool stuff, right? A response comes back, and we're going to do something. And you might be thinking, well, come on, I said reactive. Reactive means able to react to some sort of handle errors, right? Errors are these first-class citizens. I know, we'll fix it. No, it's like HTTP, obviously. We're going to fix it, and we're going to recover. And that's it, right? No. That's okay, it's a good start, but all that we've done is turn this API into this other API, and we've sort of washed our hands off it. And if all that you did in this shadow component is built a proxy in front of the device, then why did you bother? There has to be something a bit more reactive about it. So what could be a little more reactive? We already have non-blocking, so that's one tick. What else might we add into the mix? Well, let's add message-driven. How about that? Right? So instead of having these requests that arrive, we will have the shadow handle messages. And so we're going to send it this device command. And the shadow is going to turn it into an HTTP request. And it's going to run this HTTP request through the API of the device. When it receives a response, it's going to emit an HTTP response. And being stateful, right, it knows something about the device, it might then also emit device state changed. And you're thinking, that's it, right? This is the answer to everything. Well, not really, because if you look at the diagram that you see in front of you now, it looks exactly the same way that it did right at the start of the process. All these events that you sent it, that they're gone. Like, how would you know what actually happened? How would you, well, dare I say, recover? But it turns out that you might want to turn these events, these 4 events, device command, HTTP request, HTTP response, device state changed, they really don't want to be ephemeral. They want to be persistent. So we're going to dump them into some sort of journal. These events live forever. Terms and conditions apply. The only thing that comes and goes is this tiny HTTP request that we make to the device. Everything else that we keep forever. Again, terms and conditions apply, and forever could be pretty expensive if you have a lot of data. And then you're looking at this and thinking, yeah, that's kind of cool, right? We have persistent messages, which gives us the chance to replay them. And the only ephemeral request that we're making is this tiny thing at the edge that we use to talk to the device. But yeah, like one copy of the service and one copy of the journal isn't necessarily resilient. That it will go wrong. So what we're going to do is multiply these infinities, and we're going to duplicate and replicate all these events in the journal. And then we might actually duplicate all the things. What I mean by that is the state that we have in the service, we might want to write to its own database. So a service that keeps a state that represents the device will probably keep its own storage. And you could say, okay, well, no, you're looking at this thinking, oh, come on. The messages that come from these journals that I have paid for, they live on my disk somewhere. I'm able to replay all these messages and turn those into the state that belongs to the service. Why on earth would I do that? And the answer is, of course, so you can survive failures. If something breaks, you still want to continue running. You don't want to rely on this one thing, this one journal, and if that disappears, everything breaks. So that's why you duplicate data, and that's just the fact of distributed systems. Stuff gets duplicated. Okay, enough. Let's have a look at how it looks like in code. So I've taken samples from our Kafka client, and let's see how we're going to use it. So let's create this device shadow actor, and we're going to start by using our Kafka extension, and we are going to create a consumer that is convenient to use inside an actor context. So that's just the line of code. We're going to subscribe in auto-partitioning mode. So if you don't know what that is, don't worry about it now. It just means magic. Kafka is going to take care of reliably delivering the messages to us. Again, terms and conditions apply. I'll get to it in just a moment. So all that we're saying is we want to subscribe here. We want to receive messages from topic T1 and T2. What we're going to get out of it is a convenient extractor instance that allows us to turn the messages that arrive from Kafka, these batches of messages, and we can turn them into the keys of the right type and the payloads of the right type. And so what we're going to do for all the messages inside the batch, we're going to unpack the payloads, and we're going to send those payloads as messages to this actor. And we're going to do some work, and we're going to produce the output message. That doesn't look too bad, right? I mean, it fit on one slide. This is hopefully understandable code. But of course, it has this la 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 message delivery semantics, also known as at most once. You see, if something goes wrong, we just don't care about it. We never go back to a failure. Specifically, what do I mean? Well, okay, as I receive a batch of messages, let's say I've received 5 messages from Kafka, and I've unpacked them, every single one of them, and then I placed those 5 payloads into, the event store for the actor. And then immediately after that, I'll confirm to Kafka saying, yes, I have it. Those 5 messages that you sent, the batch of 5 messages that you sent me, I've processed it. But of course, the only thing that I've done is just placed it in the message queue for that actor. Now, I will deal with them here, but of course, if anything crashes in between these 2 points, I will have already confirmed it. So when this actor restarts, when this service restarts, those messages might be lost. So what do we do? What can we do to fix it? Well, let's take a look at how this offset-based delivery works. What we are going to do is not confirm every message. We're going to confirm offsets, batches of messages. So you've seen in the code on the previous slide, this is what happened. We had a batch of messages, this green one and a blue one, and we had this topic, and Kafka decided by using some strategy that it's going to send these 2 messages, this batch of messages, to this service in the middle. So it does that. Now, of course, the journal, in our case, Kafka, is persistent. The messages aren't removed from it. They still stay in Kafka, and all that we have is the 2 messages arriving at our service. And then we have this offset, right? Just number 2. We got to number 2, and that's all that we have to remember. If another message arrives after number 2, it gets sent to us. Suppose we got lucky and it gets sent to the same service. Okay, same process happens, and all that we have to do is move the offset. So it turns out that just remembering this number, this sort of watermark, how far did we get in our processing, should be enough to recover. So before we get into it, just a very, very, very brief and quick introduction. I'm sure being Reactive Summit last year, I heard some people complain that it was like Kafka Summit. So we're going to keep the theme going. Just to explain the topics, the themes, the keywords. Kafka, we have topics. Topics are divided into partitions. And then, of course, consumers consume topic partitions. In reality, you will want to replicate the topics. If all that you did is divided the topics into partitions, and one of your partitions failed, well, you'd be losing those messages. Then there's a concept of consumer groups. So multiple consumer groups can subscribe to a topic, and the offsets that Kafka maintains are unique per consumer group. So that essentially gives you broadcast semantics. And the values that go into Kafka, and you might have noticed it on a few slides previously, they're just arrays of bytes. That there is no strong typing. So what you put in is a key as an array of byte, and a payload as an array of byte, nothing else. So it's your responsibility to deal with it on the clients. All right. So let's think, before I get into really explaining how this offset-based delivery works and how we might program, let's make it a little more complicated, and let's invent a stateful service. And so what do I mean by that? Well, it's a tiny, tiny trivial state machine. And so what happens is we receive a message, and that sort of kicks us into some initial state. And then we'll receive another message, which puts us into some intermediate state, and we'll receive a final third message, which allows us to compute the output. And again, you're looking at this diagram thinking, well, okay, that's understandable, right? But we said, don't we want to be message-driven? Don't we want some insight into what this application is doing? Otherwise, we're back in the world of we have a device and all that we've done is built a really cool proxy in front of it and we just have a black box. So what we actually want to do is to emit maybe smaller intermediate messages, just to say, look, I'm in this initial state. I'm telling someone. And the cool thing is, if you have these persistent journals, you don't have to worry about who is listening. Maybe no one is listening. And that's probably a pretty good start of an implementation of a service. You're writing something, as you write your code, you might get to a point where you say, I have some interesting piece of computation that I've done. Let's emit it as a message. I don't know if anyone's interested, I don't know if anyone should be interested, but it gives you an opportunity to then expand your system a bit further. Okay, so how does it work? We have this topic with offsets, and we have our service. So when it starts up, it needs to say, okay, where do I begin subscribing from? What's this offset? And so it's going to go to this store, and it's going to read the value 3. And it says, that's where I'm going to start listening for messages. That's my starting offset. And so it does just that. And sure enough, message at offset number 4 arrives. What we're going to do is immediately confirm its delivery. We're a good, lively, responsive client. Yeah, we have another tick, right, in this reactive world. So we're going to mutate our state, and we're going to move on to the next step, which means we are waiting for this message in the intermediate state. So we're doing just that. Sure enough, message arrives, we confirm it, mutate our state. And then the same thing happens for the third message, which allows us to emit the final output. So it's exactly what happens. We mutate our state, confirm the delivery, mutate our state. Now we're in the final state, and we can emit the output message. We have done that. We receive a confirmation that the message is emitted. And then we're going to write the number 6, which is the offset that as far as we got to this store. 6, understandably, because that's the message that we got to. So if we now crash, we know how far we got, right? The output message has been safely written. If we crash anywhere in between, well, we haven't written the number 6 to this offset store. So when we recover, we're going to go back to number 3 and replay the entire sequence. Okay, understandable, right? And everyone's looking fairly happy, or at least not completely angry. Now, the talk is called Practical Resilience. So what could possibly go wrong? Well, one of the things that could go wrong is, suppose you can't actually read the value from your offset store. We wanted to read this value 3, but that failed. So now what? You could fail, right? But could we do something else? So, what can we do? So we can think about it. We can have cups of tea and biscuits and what have you. And we're going to do something, right? There has to be something that we can do. And so the decision is that we're going to read. And the question that we have to solve is, where do we read from? So what really choices do we have? Well, we can start reading right at the end. Okay, that's possible. Or we can start right at the end minus some offset. So we're going to go, okay, we have 10 million messages. We're going to go 10 million minus 42. Why 42? I don't know. But you know your system, right? You can take that choice. Or we can start reading right at the beginning. That might work for you. That might be too much reprocessing. So actually, I can't give you the answer, right? You are all waiting for this magic number. I don't have it. But the question that you need to ask that will reveal the number is, what would be too much reprocessing, or what would be too little? If you do too much reprocessing, you will duplicate the effort. You might duplicate the output messages. If you do too little, meaning you go right at the end, you might actually be ignoring messages. I don't know, depending on what kind of system you write, that gives you the right answer. Okay, never mind. So we picked the right strategy. You picked the right number. Everything works. We received our 3 messages, went through the state machine. We computed the output result. We published the output message. And so now we want to write number 3, right? But that doesn't work. So now what? Well, I can give you one more. This is my favorite British strategy. called la 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 la. Everything will be fine. Let's just ignore everything. Nothing bad could possibly happen. Now, the question, like, how long can you go la 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 la, everything will be fine? Well, again, I don't know, but if you ask this question, the answer will be revealed. How much rework can you afford on crash? Remember, you haven't written the offset, but your service is fine. This thing in the middle is running. You are receiving messages from Kafka, not a problem. Everything is fine. The only thing that you're unable to do is to say, how far did I get? So it's actually okay to ignore it for some time. If you ignore it long enough, then when eventually you do crash, when you do crash, you'll have to reprocess too much data, too many messages. So there you go. Those are the questions. Okay, so let's fix this code. So this is the one you saw on a couple of slides ago. So we're going to change this to be auto-partitioning with manual offsets, meaning we are now responsible. When we subscribe, we're now responsible to tell Kafka, okay, where do we subscribe from? Give me this number, this offset. Okay, that's kind of nice. Now, if we want to track how far we got, if we want to write these offsets to a journal, we need to change the messages that we extract. Now, how did that happen, right? What is this thing? Well, this is the usual magic of Scala. So we receive the consumer record and the ID, the correlation ID, and then the message that remains to be applied is the actual message. From the consumer record, we can get to the topic and the partition and the offset. So we receive it here. We change the handler a little bit, which allows us to extract this guy, the topic partition offset. We can prepare an offset repository, this thing that will magically, this database where we were writing these numbers 3 and 6 and what have you. And we're going to do that, right? Move this TPO and save it into the offset repository. But there is still a bit of a problem here, right? This produce is asynchronous. So this will not fail immediately, right? This will just begin the process of producing the message. And so what we actually have here is still, we've done all this work, but we still don't guarantee that by the time we've written the value of the offset to the offset repository, we have actually successfully produced the output message. So let's fix it. How bad can it be? Remember the tag that we had in the akka HTTP flow, this string. Well, let's change it. We're going to change this unit tag in our producer to be this topic partition offset. And then we're going to move this line one line below, and we're done. No, we're not. There's one more thing that's missing, which is this, right? We're going to get this tag sent back to us. So when the producer successfully receives confirmation from Kafka that the output message is produced, it's going to repeat the tag that we sent to it. And so now we have it, right? Everything went through, and we can use the offset repository to save the offset. And so if we now crash, it's kind of okay because the output message is definitely successfully written out. Okay, have a look at that. Don't worry, there'll be links at the end. So, but this is the code that you can use. Okay. Let's keep pressing, right? This offsets repository. We call the save offset method. And if it works, meaning no exceptions, the offset is written, everything is fine, then cool. Not a problem. We can just carry on. Next message, fine, as you were. If it doesn't work, what do we do? Well, one of the things you could do is to maintain this table in memory, right? This is the answer to we couldn't write. We're going to go into a la 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 mode. And the la 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 mode essentially means we're going to keep this unwritten offsets in memory. Just a list. And, it grows, and you get the idea, right? And this could be useful. And I suppose if you get into this situation, your service could say in its health endpoint, you should say, oh, this is getting degraded. This isn't exactly performing as it should be. But degraded is maybe too broad brushstroke. Maybe it's useful to associate some sort of time to live. How long are you willing to stay in this degraded mode? Because you answer the question of how much rework can we do in case of crash. And so essentially the TTL represents the risk and the damage that would happen if your service continued. So, for the first write, for the first value, the first time you couldn't write to offsets repository, everything is fine. And then it gets slightly worse, and slightly worse, and slightly worse, until, this was so nice. Let me go back to it again. Okay, everything is fine. You keep this table, you write it, then you maintain the TTL, which keeps going down as this table grows. This is all fantastic. You have your risk that you now measure. Everything is getting fine. And then finally, when it gets to 0, you send the kill message to the sender, which triggers the actor supervision. So now this guy's parent will go, oh, wow, this guy died. What do I do? And this is plain old akka code that you're already used to writing. Okay, excellent. So you might be looking at this code. I mean, it's kind of cool because you're not at the Spring talk, so this is probably not a massive surprise. Nevertheless, you're looking at this and thinking, why an actor? And this stuff, right? There's a producer, there's this extractor, rather a consumer with an extractor, there's this offsets repository, you handle all these batches of messages, you do all this stuff, but there is no useful code, right? All that you see here in front of you is just mechanics of sending stuff in and out. Maybe there's something missing here, right? This is where your code goes. Maybe code like this. And no, I am not trolling you, this is actual Scala code. It runs, it compiles, so knock yourself out if you want to have a look. Also, heads up, Christmas is coming. If you don't have Christmas presents, anyway, I'll see myself out. So, not really, right? The actual code is the state. Remember we said the reason why we're doing actors, the reason why we're doing these shadows is because we can have state that connects to the device. So, even better, we can have mutable state, right? So when we receive a message, we can do something, but crucially, we can do that. No need to worry about thread safety in this state, device state thing that you've written. So that's why we actually do actors. And that's why we wire in all this complexity into the actor you saw on the previous slide. Okay, so let's try something different. Oh, and by the way, of course, if you don't want to do anything too complicated, if you don't have a stateful service, if all that you want to do is just a single message transforms, then consider writing some of these or using some of these Confluent Connect Docker containers. You just write a simple Java program, simple jar. You base your Docker image on this one, and then you have a reliable single message transform. You don't have to write any of the code that I have here. But if you need complicated state, if you want to emit more messages as you process, then you have to do something a bit more complicated in your code. Okay. Now, if you want to have something reliable and resilient, you want to have some reliable protocols. If you remember, what goes into Kafka are just these arrays of bytes, nothing else. Key is an array of bytes, and the value is an array of byte. So you want to be able to turn, these boxes at the top into array of bytes, send those down these Kafka topics, and of course, recreate the same stuff on the other end. And JSON, right? That will do it. Well, it could. Anything, in fact, could do it, as long as you can describe it precisely. So as long as you can have some really good schema that allows you to describe these protocols, and maybe use that schema for something a bit more fancy. I will get to that in just a moment. But before we do, okay, let me give you one, I suppose, anti-pattern that I have committed many, many, many times through laziness. And it's this. If I have two services, this service, alpha and omega, for all I care, and they have the same message, right? The service at the start receives a message that has a 32-bit number and a string. And the downstream service also wants a message that has a number and a string. It's really useful to separate them. If you use the same global shared message, then what you've done is tied these two services together. and you really, really, really don't want to do that. Now, if you're using sensible language, so I've shown protobuf here, then it's not really that much typing. But don't have a common shared message. Then you have this wonderful distributed monolith that's tied together through one protocol. And if you actually go one step further and define these protocols as Scala code, now you have a jar that they are tied together with, and it's an absolute mess. Okay, so I saw a few nods and a few smiles. That was good. I'm going to make you really angry now. This is going to be really cool. Okay, let's go. So how do you now, you have big teams, you have these two services, Alpha and Omega, and you want to communicate this protocol that Alpha uses and this protocol that Omega uses, and you want to be able to get Alpha talking to Omega. So how about we get these two services, Alpha and Omega, to somehow share this one common code protocol repository? This is the anger going, right? You might be thinking, well, wait a minute. Isn't a microservice supposed to be its own complete island, right? It shouldn't share anything with anyone else. And so this probably makes you really angry. You think, well, no, wait a minute. I have this protocol directory where all these protocol lives, and the only mitigation I can give you is they're not actually Scala code or Java code, they're just these abstract definitions in protobuf, and Alpha and Omega generate their versions of the protocols. So why on earth would you do that? Well, the way we've done it is that we've separated, of course, Alpha and Omega into separate GitHub repositories, and if there's a pull request to this one, everyone pays real attention. That's a big deal. Someone wants to change a protocol. So everyone really should say, oh, well, is this going to break my stuff? Are we introducing a version? Are we introducing an incompatible change? And this turned out to work really well for us, as long as we keep to the discipline of not actually committing any code that's generated from the protocols into the protocol repository. Okay, so hopefully you're less angry now. When it comes to code, and we're going to look at Scala code, all of you fancy Java and Swift and C++ people, I'm sure you have your own tools. But the way it works is we wire in a protobuf generator. We give it access to this .1up protocol, which allows it to generate the case classes based on the protocol definitions we have. The service can have its own private protocol. So even if you have something like an internal messaging in your service, you should still use the same strong protocol definition. You hook up a protobuf generator, so none of these things, of course, get committed to your source code repository. They get generated at build time. They get spat out into this protobuf generated directory inside target, which is actually a really useful thing to do, especially if you use other plugins in SBT that generate directories, generate files at compile time, like build info. And you add a few library dependencies, and you're good to go. So even if you haven't ever seen a protobuf definition, hopefully this isn't too difficult to read. There's a name of it and a couple of fields, a number and a map and a string and an array of bytes. So that's kind of readable. What you get out of it is this. That's not too bad, right? It's just the same old case class with a final keyword. We like that. And then, of course, you get this. But don't worry, this is generated code. You don't write this stuff. Some machine writes it for you. What you do get is actually, if you ignore all of that generated mess, you get something that's fairly sensible. Remember, final case class with the parameters. The comments in your protocols get turned into a reasonable Scala doc. And of course, you can turn an instance of this response to a protobuf wire format that you can send down these Kafka topics. You can turn it into JSON. You have a description of the protocol, so you can do this same thing, and you can have, if you like, strongly typed, well-described JSON out of your HTTP response. And of course, it goes the other way, as you would expect. Okay, so We can have these services. We don't have ephemeral messages. We can recreate state. We can manage these offsets. This is all good. The services talk to each other over strong protocols. And of course, you can use that tool to generate all your SBT and Scala stuff. So let's add one more thing. Let's add these villains. So we're going to have 3 villains, 3 services that actively try to break the thing that you've written. So I now have this topic, a couple of services, and we're going to have this chaos monkey service, and we're just going to delete a few things. And then we're going to have another villain that generates this sort of alien non-user load, which is actually quite useful. What you might want to do is to start a system, and even if no one's using it, you want to see something going through it. And then we'll have one more service. I had to borrow these Unicode characters. They're brilliant, right? And it generates not quite ideal payloads, not quite ideal messages. And you want to discover what happens when your services receive really broken data. So let's take a look at it. This one is easy. Well, it isn't, but you can go to other talks that describe precisely how you should kill your dependencies and what you should do when they disappear. And actually, in code, if you think about it, we are sort of trained. We know how to deal with this. We are used to thinking, well, this database might not be there. We can, wrap it in, I don't know, try and catch and some sort of recovery strategy. It's relatively easy to imagine what happens when a service is unreachable, totally unreachable. Connection denied and no route to host and that sort of business. What's more difficult, of course, are the 2 remaining services. And so I have this one, sort of alien load, but turning into popular culture, I suppose we should call it a probe. So we have this service that can generate normal production-like traffic, and it can hit our services with it. So we could write code like this, right? The same stuff that you've seen on the first slide, except that, of course, you can do with your regular health monitoring service. Why should you want to write code in Scala? Okay, fine. So let's just generate this synthetic load every 20 seconds. So we're going to create an actor, and every 20 seconds, we're going to send a GET request to this health endpoint. Okay, this is how it works, right? You get all these successes and failures. That's kind of nice. But again, your health monitoring service can do that. Surely, if it doesn't do that, then it's really broken. It should be able to ping an endpoint every 20 seconds. So how about this? Instead of using these units and strings as the tags, how about we come up with some sort of expectation of what should happen? So I make a request, now not just to a health endpoint, just valid request, and now I would like to write code that checks that some expectation is met because I was able to observe the system as it runs in reality. So now we have something a bit more interesting. So if a response comes back, it comes back with the expectation. I can compare it and I can emit messages that say, okay, this works or this doesn't work. Same for failures. Now, where do these expectations come from? Where do you get this load? Well, you can try this tool, which through some sort of networking magic, I'm going to say, it's another Docker container that you can run alongside a service that's already bound to, say, port 8080. You can bind this Go replay tool to also port 8080, and it will just write the same traffic. It's not a proxy. I actually don't precisely know how it does it, but you can write all the HTTP traffic alongside it. So that might be the source for your expectations. But in case of our system, remember we journaled all the things. We actually have them. We have these HTTP requests and we have these HTTP responses that we can use to build these expectations. So that's a really good idea to try, and that will give you a baseline measure. You start up all your services and then you run this additional probe service, And now you know that all your components are running. You can measure latencies, you can measure the expectations. So that's kind of good. And it's also the first service that you kill when you need to scale up. Your service is running, and let's say this alien service generates 5% of your load. When you need to scale up, first step is to pause this one. And that gives you immediately 5% breathing space to scale up all the other services, and then you resume the operation of this service. Okay, that's kind of nice. How about this one? Garbage in, exceptions out. Now, we actually tried that, and we found that our services are failing in very, very surprising ways. So let's see. We have this device actor. You've seen all of this stuff, except now we can schedule some commands to run. And we have this device request protocol alongside it. Now, because we have this protocol and because of the tooling that's around the protocol, we can inspect the protocol. And so we know the types. We know that there's a string. We know that there's an array of bytes and some sort of enum. That's kind of nice. We can also use some sort of heuristics around the names. We know that a field of type string with the name URI is probably a URI. So we've sort of encoded these common sense rules into our generator. And so we can generate payload of the right type, of the right protocol, just by inspecting the types, sprinkling it with a little bit of heuristics. So we can generate this. Okay, that's kind of nice. What's of course more interesting is to generate broken payloads, like this one. So what happens if the date is in the past? Well, this crashes, because now you have negative finite duration. Okay, not great. What happens when you break the date? Month 13, that crashes. What happens if you go a little bit further? These are Unicode strings after all. You can generate anything you like. So this is not going to be too pleasant. That's not an HTTP method. This stuff that falls down are UTF modifiers on the characters. This is an interesting URI. I wonder where that comes from. /%30. What could that possibly be? Let's leave the empty map. If this is the content type header of something, that looks a bit suspicious. That doesn't look like content type at all. This might actually do something a bit malicious. This is some sort of multi-byte Unicode string. Anyway, problem is, your system will now crash there. Okay, fine, not a problem. But remember, this device request gets scheduled to run at some point in the future. So if you have this thing running in production, you have a message, you receive it, you process it, everything works, and then your system crashes at some point in the future when this scheduler runs. That's a pretty horrible thing to debug. In fact, let's try a few things. This is what we've seen. That's an easy one to fix, right? This is the exception that our generator gave. This sort of winky meh space is not a good time zone, really isn't. Okay, that's easy. We've seen this. That's fun. There is some sort of weird Unicode modifier at position 11. Now, I would really like to be on the receiving end of your support team when they get a log message like that. Or dare I say, then someone phones you and says, I have this error. And you go, what's wrong with you? This is perfectly good. Or it gets slightly worse, and you get this. That's fun. So imagine you receive a request, everything runs, you schedule this command to be executed, and then 5 minutes later, your JVM crashes. Would you suspect your code? No, of course not. It's not your code. It's some bug in JVM. Except, well, it's still your problem. You have to get the service running. Or, dare I say, this thing actually succeeds, and there is some sort of struts service at the end, and you actually make the request. So in the first three cases, your services are spinning up and down like, mad poodles, because they crash, and then, maybe you're running in Kubernetes or something, they get restarted, and then they crash again. Remember, we guarantee that these messages will be delivered because we have them in an offset. It's a mad world. And in the last case, of course, credit reports, anyone? But have a look at this. We base a lot of our strings on this repo, and there is a wonderful collection of naughty strings, which are also safe for work. It's absolutely brilliant. Don't worry, again, I'll have all the links at the end. So I had this slide actually in the evening, but I'm jet lagged, so it's evening for me anyway. So we build these complicated services. This is the kind of stuff that we build. Stuff that has journal that is replicated because we want to get, we really don't want to lose messages. We have local storage in each of these services. We have strict protocols, we have good APIs. So now that we've ended up with this thing, right, which is a complicated system, how do we ensure that at least when it runs, we're able to remain, sane? Well, we should really build reactive components. So think about back pressure, think about being really non-blocking, think about being event-driven or rather message-driven, and think about being elastic. You really want to be able to scale in and out. You really should limit these ephemeral messages. Remember the slide right at the beginning when I said, okay, let's receive a device command, emit a message, and emit the HTTP request, emit the HTTP response, emit the device state changed. These things cannot just disappear. You want to keep track of them. You want to store them forever. Again, terms and conditions apply, and you'll have to spend money for forever. You really have to use strict protocols. I don't care what you use, right? Protobuf, Avro, your choice. But the worst thing that you can do is to define your protocol, is to derive your protocols from case classes and some automatically derived marshallers. That way lies ruin. You have then no idea what your service's input and output looks like, and you've actually disconnected. So you document it, right, for sure, right? But you've disconnected the documentation from the code, and mistakes happen. You should inject network partitions. So you have your system running, and the first thing that you want to do is to start killing things. Kill network. And you can start really, really low key. Just run it in Docker Compose and pause the containers. That might get you going. You should definitely probe using live traffic and live load profiles. Again, not all requests are the same. Some requests might result in doing more work. So if all that you do is just probe for the health endpoint, that really isn't enough. Send these requests. But then you say, okay, well, what if I send a destructive request? I don't want to do that. Well, no, but surely you're using some sort of security around your services. So this probe service should be able to only obtain a token that allows it to do non-destructive work that your other services should check. You should definitely deliberately inject faulty and malicious data. That's probably the best thing and the most fun thing you can do with your system. And in one day, you will find out so many, I'm going to call them bugs, but unexpected features that you wouldn't find in weeks of production. Absolutely fantastic. And it's really useful to define degraded operation. What does it mean when a service says, I'm degraded? How long is it okay for it to stay degraded? Do we mean degraded and not accepting requests? Degrading and will still do the work? Degraded and will take more time? So think about what that means and report it accordingly. Finally, if you haven't been snapping quickly enough, there's one more opportunity, but don't worry, I'll share all the slides. So the Kafka client and SBT cake, which encodes this common practice of building component Scala PB for protobuf generators, Go replay for this pseudo magic HTTP traffic slurper, list of naughty strings, and bits of Confluent platform. So we're right on time. Now, we've done all this work for our big clients, so I'm not entirely sure I can answer all of your questions without saying, and you can't leave this room, but come and talk to me person to person. I'll give you all the details that I can. So thank you very much.